Good afternoon, class. Here's chapter 2, limits, section 2.2, limits of functions at infinity. Limits of functions at infinity. We covered 2.1, limits of sequences, and now 2.2, limits of functions at infinity. So here's the synopsis of what we covered. A sequence is an ordered list of numbers or function f whose domain is the set of natural numbers 1, 2, 3 to infinity, also known as positive integers. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in the long run. When the limit of a sub n as n approaches infinity is L, we say that a sub n converges to L. When the limit of a sub n as n approaches infinity is infinity, or negative infinity, or DNE does not exist, we say the sequence diverges. To find limits, simply plug in the value and observe. We'll go over that today more specifically. Some of the theorems we learned, the limit of r to the power of n as n approaches infinity depends on the value of r. If that is between -1 and 1, the answer is 0. If it's 1, the answer is 1. And if it's larger than 1, the answer is infinity. Another theorem we looked at, the limit of 1 over n to the power of p as n approaches infinity is 0 for p larger than 0. What it means is that if you have a fraction, when the denominator gets larger and larger and larger, the fraction gets closer and closer to 0. Geometric sequence, when we add them up, becomes a geometric series. S sub n equals the summation of a r to the power of n minus 1 as n goes from 1 to infinity. It's a plus ar squared. It continues indefinitely, and it has the formula a times 1 minus r to the power of n over 1 minus r. We have to take the limit of that expression as n goes to infinity. When r is between -1 and 1, according to this, r to the power of n goes to 0, and therefore we get a over 1 minus r. So for the geometric sequence, b sub n plus 1 is r b sub n. This is the recursive format. B sub n equals b sub 0, r to the power of n. By the way, b sub 0 or a, depending on the text, that is the explicit format. If we use the same thing and we add a constant, such as giving medication at a time step to patients, the result will be the same as this one plus this factor. So the same as this one plus c, the constant, times 1 minus r to the power of n over 1 minus r. And of course, a or b sub 0. So this formula is the same as this one. We use either a or b sub 0. So that is extremely important to understand what's going on. So this is the synopsis of what we covered. Now, the summary of what we are going to cover is here. 2.2, limits of functions at infinity. Here's the summary. Definition. Horizontal asymptote, short HA, of the curve y equals f of x has this equation, y equals L. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is L. And again, you remember this, the limit of 1 over x as x approaches infinity is 0. No limits of functions at infinity, this ends up being 0. The limit of 1 over x to the power of p as x approaches infinity is 0, as long as p is larger than 0. Those are some of the stuff we have seen. This is an exponential function when the base is larger than 1. This is an exponential function when the base is between 0 and 1. In general, an exponential function has the form y or f of x equals b to the power of x, where b is positive, can't be 1. When it's between 0 and 1, it's an exponential decay. When it's larger than 1, it's an exponential growth. For example, when we look at e to the power of x, remember, let me just write that. Y to the power, y equals e to the power of x. That's an exponential growth, okay? Remember, e is 2.71 and it continues indefinitely. And so the limit of e to the power of x as x approaches minus infinity is 0. So for the exponential function, for any function such that b is larger than 1 exponential function, okay, any exponential growth, this is true. And for any exponential growth, also this is true. The limit of f of x as x approaches infinity is infinity. For any exponential decay, the limit of e to the power minus x, for example, as x approaches infinity, is 0. And these two practically show you that the horizontal asymptote for both of them is having the equation y equals 0, which is the x-axis. However, limit of f of x as x approaches minus infinity is infinity. So a shorthand notation for those would be something like this. When x gets smaller, y, remember y or f of x are the same, it gets larger. In this example, when x gets larger, so does y. And you recall from algebra, y equals x cubed looks like that. And therefore, the limit of f of x as x approaches minus infinity is minus infinity. And the limit of f of x as x approaches positive infinity is infinity. And this is known as what? The end behavior in algebra, in college algebra, pre-calculus unit. We want to find this limit. We have seen this before in the case of a sequences. Because x is approaching infinity and you're dealing with a rational function. Remember, rational function is the one that the bottom and the top are both polynomials. The top and the bottom, okay? And polynomials are in the form of a sub n, x to the power of n, all the way to a sub 0, okay? And the exponent they have to be whole numbers, okay? That's the definition of a polynomial. And so we are going to divide by highest degree term in the denominator, namely x squared. When we do that, and we are going to do term by term, this is what we get. Now, of course, at this point, I go to the result, but I want to show you the limit laws or limit properties. So in this case, we apply the limit to the top, we apply the limit to the bottom separately. That's the concept known as limit laws. Then the top has three parts. We cut the limit into three parts, the same thing for the denominator. And again, this is known as using limit laws or properties. And because x is approaching infinity, please understand, you have a fraction, the denominator is huge. So this is 0, 0, 0, 0. And I would have gone from here straight to here, which makes it 3/5. And everybody knows 3/5, by the way, is the same as 0.6. So if we were to graph this function, y equals 0.6 or 3/5 is the equation of its horizontal asymptote. The graph gets to the horizontal asymptote and runs along it. In this part, it hits it, it crosses it, and it comes back down. Also, the limit of f of x as x approaches minus infinity is 3/5, because when x approaches infinity or negative infinity, the technique is the same. Divide by highest degree term in the denominator. That's the technique we use. Infinite limits at infinity. The notation of limit of f of x as x approaches infinity equals infinity is used to indicate that the values of f of x become large as x become large. Similar meanings are attached to the following symbols. Limit of f of x as x approaches minus infinity is infinity. Limit of f of x as x approaches infinity is minus infinity. Limit of f of x as x approaches minus infinity is minus infinity. So in essence, they are giving us the concept that was just discussed. Okay, everybody? So I believe it's pretty straightforward. They all refer to the same concept. What concept is that? If you recall in algebra or in pre-calculus, we call this the end behavior of a function f of x. The end behavior of the function f of x. So if you look at all of these functions, y equals ln x, y equals square root of x, y equals x squared, y equals e to the power of x, the limit of f of x as x approaches infinity is infinity. That means the first quadrant. What is the difference? Some are approaching infinity faster than the others. For example, y equals ln x is the slowest, y equals e to the power of x is the fastest approaching infinity. But nevertheless, they will approach infinity. A function that you're all familiar with is the cube function, where this refers to the end behavior of the function, the first and the third quadrant. The limit of f of x as x approaches minus infinity is minus infinity. The limit of f of x as x approaches infinity is infinity. Okay, so I hope everybody remembers that. That's a very important concept in algebra that we should remember. The end behavior of the function. Now, we want to find the limits. Algebraically, what do? We just plug in and observe. So when we plug in and observe, what happens? Well, when we plug in, we may get to a number. That's the limit, and we are done. We may get to 0 over some number. And the answer is 0. And we are done. It's 0. We may get to some number over 0, and we have to figure out in that case if it's going to be infinity or negative infinity, because a number over 0 ends up being one of the two, infinity or negative infinity. However, in calculus, most of the time we end up with a form known as indeterminate forms. The forms that are 0 over 0, infinity over infinity, infinity minus infinity. Those are called indeterminate forms because anything can go. 0 over 0 or infinity over infinity is not necessarily 1. It can be 0, it can be infinity, it can be some number. You have to work it out. Infinity minus infinity is not necessarily 0. Could be 0, infinity, or some other number. You have to work it out, and I can't emphasize this enough. In calculus, most of the time we end up with indeterminate forms. So again, we are looking at an example that we practically are pretty comfortable with. We have seen similar examples because the variable now x, y, z, n, in this case t, is approaching infinity, and we are dealing with a rational function. The technique is to divide by highest degree term in the denominator, namely t squared. And we're going to simplify. This becomes 5 over t. This remains. This becomes 1. This becomes 2 over t. This remains. And because t is approaching infinity, 5 over infinity, 7 over infinity squared, 2 over infinity, minus 1 over infinity, all of this go to 0, 1 remains. And so what you're dealing with is 0 over 1. And 0 over 1 is 0. It's important to understand why I wrote the 1 in the denominator, because 0 over any number other than 0 is 0. Even 0 over infinity is 0, okay? But if you have 0 over 0, it's indeterminate. You have to work at it. By the way, if you were to plug in, I want you to know that if you were to plug in, you would get infinity over infinity, everybody. Okay. Same thing here. If you would plug in, you get infinity over infinity, which is indeterminate. So the technique is, because t is approaching infinity, you divide by highest degree term in the denominator, t. Let's divide everything by t. So every term in the numerator as well as the denominator must be divided by highest degree term in the denominator, which is t. And we are going to simplify each as follows. This becomes t. This is 2. This doesn't change. This is 5. This doesn't change. And when t approaches infinity, we'll replace the t with infinity here. This one, when you replace it, becomes 0, 7 over infinity, 7 over infinity. This is 0, this is 0. And what is important for everybody to see, infinity plus 2 or times 2 or minus 2 or minus 10,000, the numerator is still infinity. Infinity divided by 5 or 5 billion or times 5 or times 5 billion makes no difference. It is still infinity. Okay. That's important for everybody to know. The limit of the square root of x squared plus 1 minus x as x approaches infinity. I hope you see this is infinity minus infinity. I want to explain that so everybody can see why this is the case. If you plug in, this is infinity, square it plus 1 and take a root, it is still infinity, because I have mentioned it before. If you have infinity to the second power, if you take the root of infinity, it makes no difference. All of them are infinity. Infinity minus infinity is an indeterminate form. So you need a methodology to solve that. The method is using conjugate, where the conjugate of a plus b is a minus b, and you know the product is a squared minus b squared. See, the opposite of that is minus a minus b. We are not looking for the opposite of that. We just write the opposite of one of them, normally the second one. So a plus b. The conjugate is a minus b. The product is a squared minus b squared. So the conjugate for this guy, you change this negative sign to a plus sign. So you're going to multiply and divide by. Why do you do that? Because we don't have a right to multiply by anything except 1. And as you can see, this expression is equal to 1, and that's fine. We can multiply by 1. So if I extend the fraction bar, the denominator remains as square root of x squared plus 1 plus x. The numerator, according to this formula, a squared minus b squared, this gets squared up, minus this gets squared up. We can cancel those two. And we get the limit as x approaches infinity of 1 over square root of x squared plus 1 plus x. And I hope you realize. When you plug in infinity, infinity squared plus 1, you take your root. This becomes infinity, this becomes infinity. 1 over 2 infinity or 10 infinity. The bottom is infinity. Any number over infinity is 0. Okay? But again, you couldn't assume that is 0 because I will look at examples where this is not the case. Okay? So we are drilling, we are looking at different examples, and we are getting familiar with the methodology to take care of limits. We want to find the limit of 12 over 4 plus 3e to the power of minus t as t approaches infinity, and of course, just plug in. And when we plug in e to the power of minus infinity is 0. And why is that? E to the power of minus infinity is 0. Why is that? I remind you that a to the power of minus m, the negative exponential is 1 over a to the power of m. Therefore, e to the power of minus t is 1 over e to the power of t. So 1 over e to the power of infinity means 1 over infinity. And any number over infinity is 0. That's why this is 0. 12 over 4 is 3. So this is 0, by the way. Now, if you plug in here, and you can try it, you get 5 plus e to the power of infinity at the top. 5, let me just write that, 5 plus e to the power of infinity at top, 4 minus 3 e to the power of infinity at the bottom. And I hope you realize you do get infinity over minus infinity, which is indeterminate. Okay. So what is the technique? This is not a rational function. It's a fractional function. Okay. Transcendental function, they call it. In the case of a rational function, we divide it by highest degree term in the denominator. Because t is approaching infinity, we are going to divide by highest value in the denominator, which is e to the power of t. We divide everything by e to the power of t, and of course, this is 1, this is negative 3, the other ones we write. This goes to infinity. So 5 over infinity, this goes to 0. This goes to infinity. 4 over infinity is 0. So 0 plus 1 over 0 minus 3 is negative 1/3. So 0 plus 1, this is 0. 0 minus 3, this is 0 because t is approaching infinity. Negative 1/3. So conceptually, we do the same thing to this example that we did to rational functions. Because t is approaching infinity, we divide by highest degree term in the denominator. In this case, when you plugged in, you just had the answer. What happens here? If you plug in, you get infinity squared minus infinity, which is infinity minus infinity because infinity squared is the same thing. So what is the technique? We multiplied by conjugate in the previous page. Now we are going to use factoring. So factor the x out. It results in infinity times infinity minus 1. I hope, again, you realize infinity minus 1, infinity minus any number is infinity, and infinity times infinity is infinity. So the answer is infinity. In the previous page, a similar question, we ended up with 0, and now we have infinity. So anything can go. Rational function, the limit of x squared plus x over 3 minus x as x approaches infinity. If you plug in, class, if you plug in, the top is infinity squared plus infinity, which makes it infinity. The bottom is 3 minus infinity, which is minus infinity, and it's indeterminate. So what was the technique? Because x is approaching infinity, we divide by highest degree term in the denominator, namely x. We divide everything by x. I'm showing you various notations. So the top becomes x plus 1 over 3 over x minus 1. This, when you divide by x, becomes x. This one divided by x becomes 1. This is 3 over x minus 1. And so if you plug in, this is infinity. This is positive 1. 3 over infinity is 0. 0 minus 1. So here's the interesting part. The top is infinity. The bottom is negative 1. So the answer is negative infinity. So the thing that is important, you got to be careful with the sign. Okay. So if you wanted to go with the easy way out, the degree of the numerator was larger than the degree of the denominator tends infinity. It happened to be negative infinity. Okay, so you want to be very careful with that concept. Anybody feels like reading this for us? Okay. The Pacific halibut fishery has been modeled by the equation B of t is 8 times 10 to the power of 7 over 1 plus 3 e to the power of negative 0.71 t, where B of t is the biomass, the total mass of the members of the population in kilograms at time t. We want to find the limit of B of t as t approaches in infinity, and we want to know what that means. What is the significance of that? So let's take a limit. Can anybody give us the answer based on many examples that we did? T approaches infinity. So this is approaching 0. 3 times 0 is 0. So the answer is 8 times 10 to the power of 7. Why is that? I want to show you the reason. This part, everybody, becomes 0 because e to the power of minus 0.71 t is 1 over e to the power of 0.71 t, and you are going to replace the t with infinity. E to the power of 0.71 times infinity is 1 over infinity, which is 0. Now 3 times 0 is 0. That's your answer. Very straightforward. What does it mean? In a long run, the Pacific halibut biomass will be 8 times 10 to the power of 7 kilograms. 8 with 7 zeros, 80 million kilograms of Pacific halibut. That's the meaning of it. Very straightforward. So the key was to remember the methodologies that we've used. This, because of the negative, means minus 0.71 times infinity and goes to 0. A tank contains 5,000 liters of pure water. Brine that contains 30 grams of salt per liter of brine is being pumped into the tank at a rate of 25 liters per minute. show that the concentration of salt after T minutes in grams per liter is B of T equals 30T over 200 plus T. So the first part is algebra, has got really nothing to do with this course. We just want to verify that they gave us the correct function. So to do so, we want to show that the concentration of salt what do we mean by concentration of salt? The amount of salt over the amount of liquid. That is the definition of a concentration class. So the concentration of salt means how much salt over how much liquid. That's the meaning of it. So all we have to do, if we find the amount of salt over the amount of liquid, we put it in and we get to the equation. So let's start with what is given. 25 liters per minute of brine. So let's discuss the amount of liquid. So we have 5,000 liters and we are adding this much, just for the sake of argument so we understand. If we add this much only over the course of 1 minute, so we are adding 25 liters of brine. If it takes us 2 minutes, 25 times 2 liters of brine. If we do this for 10 minutes, so we let it run for 10 minutes, we are adding 25 times 10 liters. But we are going to do it over the course of T minutes. So 25 times T liters of brine. So how much after T minutes? Amount of brine added is 25 times T liters. This is how much we are adding for the amount of liquid. What are we adding it to? Whatever we had in the first place. Brine contains 30 grams of salt per liter. So 1 liter has 30 grams of salt. 2 liters has 2 times 30 grams. 10 liters has 10 times 30 grams. So what is the amount of salt added after T minutes? What about after T minutes? Well, after T minutes, we have this many liters, and each liter gives us 30 grams. So what would be the amount of salt? This much, 25 T, times this much, 30 grams. So the amount of salt added is the product of these three, which is 750, 25 times 30, 750 T grams. So the numerator is 750 T grams. But what about the amount of liquid? Well, here's the amount of liquid added to what? To whatever we had. What did we have? 5,000 liters of pure water. So this goes to the top, this goes to the bottom, and the units are grams per liter, just the way we have it. And so this doesn't look like that, but you can see clearly both of them are divisible by 25. If we factor out the 25, we get exactly what they gave us. So we just proved B of T is 30T over 200 plus T. But this is calculus. What happens as T goes to infinity? That means, let us find this limit, everybody. to find the limit, because t is approaching infinity, and we are dealing with a rational function, we divide by highest degree term in the denominator. We divide everything by it. And what do we get? This one becomes 30. This remains. This one becomes 1. Because t is approaching infinity, 200 over infinity is 0. You get 30 over 0 plus 1, or 30. And don't forget the grams per liter as the units. Now, here's the importance of this. What does it mean? This is extremely important, class. We had 5,000 liters of pure water. We had a lot of water. The concentration for the brine was 30 grams of salt per liter of brine, and we got the same answer. Why is that? Because in the long run, if you add brine non-stop, you never stop, it eventually becomes so much that 5,000 liters becomes peanuts, becomes nothing compared to the volume of a brine being added. Brine takes over so much so that everything in essence becomes brine. So in the long run, all the liquid turn into brine. And that is extremely important to understand. And the implication of this concept, for example, when it comes to environment. Okay.